Hello, everybody, and welcome to the TechInsights webinar presentation on Space Power Beams, shorten the trek to gain the edge in 5G transceiver design and manufacturing. My name is Scott Parker, and today's presentation will be delivered by John Sullivan and Cal Nolan, whom I'll introduce to you in just a moment. TechInsights exists to support a fair marketplace where semiconductor and electronics intellectual property can be innovated and monetized. Our capabilities in reverse engineering and technical analysis, combined with the knowledge and skill of our in-house subject matter experts, enable us to prove patent value and drive the best fact-based IP and technology investment decisions. Our analysis spans a wide range of electronic markets and device types, for which we provide various levels of insight, from product teardowns to materials analysis at the atomic level. We offer a suite of subscriptions that are updated frequently with the analysis of the latest consumer products. We deliver this content through our feature-rich TechInsights platform and offer additional software solutions that provide unparalleled functionality to explore analysis and to connect technology with the IP landscape. TechInsights is your definitive source for semiconductor analysis. Today's presentation will be delivered by John Sullivan, Senior Circuit Analyst, and Cal Nolan, Senior Product Manager, focusing on mobile RF technology and analysis. This presentation was previously recorded, but you can submit questions and we will provide responses shortly after the broadcast. To submit a question, click on the chat bubble at the top left of your screen and enter your question in the text box. And now, over to John and Kyle.
Thank you to all who are joining this webinar today. I'm Kyle Nolan, and I'm the product manager for our mobile RF channel. And I must say, I'm very happy to see that we have a broad mix of people from around the industry, ranging from pure play foundries to chipset designers. And our hope is that by the end of this session, you'll have learned something interesting, and with any luck, you'll find our analysis aligns well with some of the problems you're trying to solve today, whether it is design or manufacturing related. So we only have 30 minutes. The agenda is quite short. I'll provide some brief background on our transceiver content and coverage before passing it over to John Sullivan, who will conduct the presentation on the Qualcomm QTM052 mmWave antenna module. And then he'll hand it back over to me so we can wrap it up. Now, a very quick introduction. We have been profiling a lot of transceivers, certainly every 5G transceiver we can get our hands on. And as far as I know, we have full coverage on 5G millimeter wave transceivers that are generally available for consumer purchase. And as you might expect, these components are quite interesting. As everyone knows, the real estate inside cellular-enabled handsets is at a premium. More cameras, new sensors, bigger batteries, and now more antennas are competing for space and power. What might be even more interesting to some joining us today is seeing how one of the leading chipset providers in Qualcomm is solving 5G millimeter wave problems differently from your organization, or perhaps where there's a lot of similarities. So without further ado, I'm going to hand it over to our senior circuit analyst, John Sullivan, who will walk you through some of our findings on the QTM052 millimeter wave antenna module from Qualcomm.
Thank you, Kyle. 5G is well and truly upon us, but millimeter wave 5G is still really in its infancy. FR1 5G frequency ranges are for the most part set and allocated in the sub-6 GHz range. FR2 5G frequency ranges cover frequencies above 6 GHz, which are loosely classified as millimeter wave frequencies, although technically millimeter waves are over 30 GHz. The new radio band N260, which is 27.5 to 28.35 GHz, is allocated and in use in the US with Verizon, and N261, which covers 37 to 40 GHz, is soon to follow. In this webinar, I'm going to examine the architecture of a transceiver that operates at these frequency ranges. TechInsights has torn down several millimeter wave enabled handsets. These first handsets are what I'm calling the first gen millimeter wave handsets, as they were the first ones out and they used the first generation of millimeter wave transceiver technology, namely the Qualcomm QTM052 millimeter wave antenna module. The second generation millimeter wave enabled handsets use the Qualcomm QTM525, which is Qualcomm's second gen solution. Both of these antenna modules can accommodate N260 and N261 frequency ranges. In this webinar, I'm going to focus on the millimeter wave transceiver architecture implemented with the QTM052 module that is found in the Samsung Galaxy S10 5G handset. I will describe the different stages of the analysis that were taken to build the overall picture of the mmWave transceiver architecture from the antenna to the modem. We start with the teardown of the handset. This is the Samsung Galaxy S10 5G. The image shows the phone with the back panel removed to expose the antenna modules and the main PCB. From the teardown, we observe 3 QTM052 mmWave antenna modules. From the image you can see the placement of the modules within the phone in relation to the mobile SoC. 2 are placed to radiate out the sides of the phone near the top and bottom, and the third is placed at the top and radiates out the back of the phone. These modules are then connected via a tape connector to the main PCB, where they are then ultimately routed to the modem, which in this case is the Qualcomm STX50M 5G modem, indicated by the yellow box here. The component is on the other side of the PCB. At this point we know there is a phased array of antennas that speak to the modem. The first question is how is the RF path partitioned? Before we dive into what is observed in practice in the handset, let's examine a few of the theoretical options available. Option 1 in the top left is the RF interface. This solution has a simple IC within the phased array on the left. It would only have a power amplifier / LNA and the phase shifters. No need for a phase lock loop, therefore no reference clock routing issues. There would be long mmWave signal lines routed between the phased array and the modem, making large signal loss at these frequencies likely and making it hard to maintain good matching. Option 2 is the IF interface. The phased array chip is now more complex. It has the PA LNA, phase shifters, phase lock loop, and the mixer in order to convert mmWave down to intermediate frequency. Long IF lines would then be routed from the phased array to the modem, which would result in less loss and easier matching. This option will also need a second RF chip to convert from IF to baseband, which is then coupled to the modem. Option 3 is the baseband interface. This solution places a very large chip inside the phased array. Large bandwidth baseband signals are routed on the PCB to the modem. These could be analog or digital. Option 4 is the IF interface to modem. This solution is similar to option 2, except that the IF from the phased array is routed to the modem / SoC that integrates the IF RF chip and the modem. And this integration can be in the form of a multi-chip package or integration onto a single die. The single die integration is desirable, but less likely as analog RF functions are still hard to implement on the lower process nodes of the modem. So, which option do we see in practice? This is the Qualcomm QTM052 mmWave antenna module. These are the top and bottom package photos. The module measures 19.1 millimeters long by 4.8 millimeters wide and 1.8 millimeters thick. The tape connector is located on the left. There is a shield that shields the dies on the module substrate on the top, and there are 4 repeated structures visible from the rear of the module, which are presumably the antenna elements. An X-ray of the module further reveals interesting information. 2 die are present in the module. The die photos of the die are superimposed on the image for clarity. The large die on the left is an RF die, and the smaller one on the right is a power management IC, or PMIC. The side X-ray reveals that the module can be divided into an upper portion and a lower portion. The upper portion houses the ICs, and the lower portion houses the antenna elements. Through-hole vias are used to connect the upper and lower portions of the PCB. These are clearly visible on the side X-ray. Now we start the reverse engineering process on the module PCB to gain a better understanding of the antenna structure and how the antennas connect to the RF die within the module. The images here show the layer stack for the module PCB. The lower portion is made up of 6 metal layers, all of which are shown here. The upper portion contains a similar number of metal layers, but only 3 layers are shown here for clarity. The antenna structure is interesting. There appears to be 4 stacked dual-phase square post-fed patch antennas. M3 holds the driven patch, which is then coupled to the M1 patch via aperture openings in the M2 layer. The M1 patch also makes use of 4 edge coupled structures. The M1 patch is connected to two vias, dual phase, that connect through the M4 to M6 layers, at which point through-hole vias are used to connect to the microstrip lines in the M8 upper portion of the PCB. These microstrip lines are then routed to the transceiver die. These images show a detail of the microstrip line that connects the patch antenna to the RF transceiver. The single-ended line is routed to the transceiver, where it splits off and connects to two pads on the transceiver die, the TX and RX ports as it turns out. There are two lines from each of the patch antennas, hence dual phase. Once we have the module PCB delayered, we can reverse engineer the connectivity of the module. To do this, we recreate the GDS2 polygons representative of all the metal layers for routing and interconnect. The top image shown here shows all the layers in one view. The different colors represent the different layers. The lower image shows only the signal routing of the microstrip lines from the antenna patches. The M3 patch layer structure is visible in the background. These 8 microstrip lines connect to the RF transceiver die that is located in the center of the module. Once we have the connectivity of the PCB extracted and the components on the PCB identified, we can essentially have a flat netlist of the PCB and create the block level schematic diagram of the antenna module. So we have our two dies, the transceiver and the PMIC. The 4 antennas are shown on the right. Note the transceiver has 16 TX and RX ports, but only 8 are used. 2 connections from each of the 4 dual phase antennas. The interface of the module is on the left and contains 2 bidirectional connection points. This gives us the first indications of the architecture used. As I mentioned earlier, there were 3 antenna modules on this phone. 2 were as I have just described, but the third was slightly different. This is the module that was located at the top of the phone and radiated outwards. This module is slightly larger. It appears to house the 4 patch antennas as well as 4 dipole antennas at the bottom of the module, as shown nicely in the X-ray here. Therefore, this module has 8 antennas. It uses the same RF transceiver as the other modules. Therefore, it will most likely use all 16 of the TX-RX pins on the transceiver die. Next step in the investigation is to examine the modem. This image shows the die photos of the dies within the STX50M 5G modem superimposed on the X-ray of the component. As you can see, this component contains 3 die within the package. The modem die is the large one in the center background. A memory die is then stacked on the modem. And there is also what looks like an RF chip off to the right that interfaces most likely to the modem. So based on what we've learned so far, we can start to build the picture of the transceiver architecture. We have 3 antenna modules, 2 with 1x4 patch dual phase arrays, and 1 with a 1x4 patch dual phase array and a 1x4 dipole array. Each module has its own RF transceiver die that presumably talks to the modem via the RF interface chip packaged within the modem. The picture of the transceiver architecture is coming together, but we need to dive into the individual chips within the RF chain to gain a more comprehensive understanding. This is the die photograph of the transceiver die within the QTM052 module. From this level, we can get an idea of the rough floor plan of the device. There are 4 repeated blocks in the 4 corners of the die. I call them the TRX quads, with some common circuitry in the center cross-shaped area. There is also a repeated block located between the 2 corner blocks on the top and bottom. Each TRX quad is further subdivided into 4 more repeated blocks with common circuitry in the cross shape between them. They are labeled here, but this is a result of the completed analysis. At this point of the analysis, though, we would only be able to speculate. The next step in the process is to reverse engineer the transceiver to a point of an understanding of the architecture of the device. Please note that this is not a detailed transistor level extraction, but rather a high level extraction of the general architecture of the device. This is the level of analysis contained in TechInsights transceiver architecture reports. This analysis takes advantage of the fact that characteristic layout features such as high-speed signal routing, inductors, AC coupling capacitors, and balanced circuit design practices are easily identified with the use of lower resolution SEM mosaics of the upper 5 or 6 metal layers and the polysilicon layer of the device. Couple this with the experience of the analyst and we can extract the high-level architecture of the device, which really is a block diagram of the transceiver, like what you might find in a datasheet if they existed, which for the most part they don't. Like the module extraction I showed earlier, the process involves recreating the GDS2 polygons for, in this case, the upper 5 or 6 metal layers of the device in order to recreate the connectivity between any identified circuit components. This image shows the recreated GDS2 layers all superimposed together. At this stage you can see some of the RF features that I just mentioned, some inductors and some of the signal routing channels. Once we have the circuit components identified and their connectivity created, we can begin to create the architecture schematic of the transceiver. This shows the top-level schematic diagram of the transceiver. The blocks are laid out in a manner that reflects the layout of the die. We can see the 4 repeated transceiver quads in the corners with a common PLL area in the horizontal strip. The 2 repeated blocks in the vertical strip serve the 2 repeated transceiver quads on the top and bottom respectively. The connections to the antenna are shown here as well. As I mentioned for 2 of the modules, only 4 antennas were used. Since these are dual phase antennas, we need dual data streams to support 2x2 MIMO. Based on how the antenna are connected, we can see the upper portion of the die is one data stream and the bottom is the other. Looking at the upper data stream, we see that the 2 antennas connect to the transceiver quad on the left and 2 connect to the quad on the right. Each quad further contains 4 unit transceiver tiles, only 2 of which are used. 4 antenna, 4 unit tiles total. Each unit tile contains a super heterodyne transceiver with an LO phase shifting architecture that converts mmWave to an intermediate frequency. The IF signals for each of the 4 unit tiles are combined and exit the transceiver quad via balanced RXIF and TXIF pads. Similarly, the transceiver quad on the right produces balanced TXIF and RXIF signals of its own. The signals from the 2 quads are then combined and pass through the IF front end block that converts to a single unbalanced signal via a balun that ultimately interfaces to the motor. The lower level details of the unit transceiver are available in the architecture report for this device, but here is a small detail of the transmit path of one of the unit transceiver tiles. The balanced transmit IF signal is input on the right. The transmit path includes a high frequency and low frequency path. For the final up conversion, each path includes a double balanced mixer. The transmit path continues in a chain of 3 tapered amplifier gain stages with RF transformer coupling between them. The balanced output of the final 4th gain stage of the 2 paths are connected together and converted by an RF balun to a single-ended signal. The image below the schematic represents the layout of the circuit. The correspondence between the schematic and the layout is apparent. You can see the 2 transmit paths with their coupling transformers and final balun here on the left. As with all TechInsights circuit reports, the architecture report allows for easy cross-probing between the layout and the schematic. This allows the user to investigate layout features that may or may not be highlighted in the report. So after the analysis of the RF transceiver and the QTM052 module, the overall architecture looks like this. 3 antenna modules with a total of 16 antennae. Each antenna module has a transceiver die that converts and combines the antenna streams at IF, at which point they are routed to the modem SoC. Turning our attention now to the RFIC that is packaged within the STX50M modem. This image shows the functional block floor plan of the device. The die is essentially split in half with a transceiver on either side of the die with 2 PLLs and common circuitry connecting the 2 transceivers in the center strip. Reverse engineering this die in a similar fashion to the others reveals the top level diagram shown here. The left and right transceivers represent the two data streams necessary for the dual phase antenna array as mentioned before. Each transceiver contains 4 unbalanced bidirectional pads. These are the intermediate frequency signals that connect to and from the QTM052 antenna module. The transceivers then convert the unbalanced IF to 2 sets of quadrature analog baseband signals for transmit and 2 for receive. This is the architecture schematic of the left side transceiver. First of all, consider the receive path. The 4 unbalanced IF signals enter this chip on the left and pass through an impedance matching circuit, then pass through an RX-TX switch network. The 4 RX path branches off to the top, at which point they are combined in what looks like a resistive combiner. The data signal then passes through a balun to generate a differential signal. The differential signal goes through an amplifier stage and another transformer. It is then split into 2 paths, each path passing first through a capacitor before going to a pair of mixers. Each mixer receives a different pair of LO signals from an LO buffer in order to generate quadrature IF signals. The in-phase and quadrature paths each pass through a respective passive filter. The filter signals then pass through an output driver to drive the external output pads, which are then routed to the modem. The transmit path receives the input transmit quadrature data on the right. The I and Q data each go to a respective mixer through a capacitor. Each mixer receives a pair of LO signals from an LO buffer. The 2 mixers have common differential outputs. The differential RF data generated by the mixers pass through a transformer. The output of this transformer is split into 4 separate paths that each pass through an amplifier and balun to convert to a single-ended signal, and then pass through the RX-TX switch network before exiting the chip via the bidirectional IF pads on the left. So with the analysis of the RF chip within the modem package, the picture of the architecture of the mmWave transceiver is just about complete. So adding to our diagram, the RFIC in the STX50M package accepts the IF signals from the antenna modules. Notice that the IF chip can accept 4 sets of IF signals, so in theory it can connect to 4 antenna modules. In fact, the Motorola 5G mod phone, which is arguably the first mmWave phone, had 4 QTM052 modules in it. So in this case, the IF signals from the 3 QTM052 modules are combined and converted to and from quadrature analog baseband. The final piece of the puzzle lies in the modem die itself. This is a polysilicon layered die photo of the STX50M 5G modem. The boxed off area here are what we believe are the data converters that convert the data to and from digital baseband. This has not been analyzed in detail, but the layout of the block and its location in relation to the IF die, as well as the process of elimination, all point to these being the data converters. This completes the picture. The antenna module combines the signals from the antenna and the module and converts them to IF. The IF is routed to the RF-IF chip within the modem package, where the IF from the individual modules are combined and then converted to baseband. The baseband is then converted to and from digital within the modem die itself. As expected, this is essentially option 4, the IF interface to the modem that I mentioned at the beginning of the presentation, with the exception that the data converters were embedded within the modem die itself. All of this analysis was pieced together from the transceiver architecture analysis reports on the relevant individual dies available from TechInsights. To conclude, I just want to touch on the second generation of mmWave antenna module and give a little sneak peek. As I mentioned earlier, the second generation of mmWave enabled phones used the QTM052 antenna module. This module has been redesigned to a certain extent. First of all, the form factor has changed quite a bit. It is slightly thicker, it's longer, but less wide. This shows the QTM052 and 525 solutions side by side. It shows the QTM052 and 525 solutions side by side. We just discussed the QTM052 solution with the transceiver in the module and the IF die within the X50 modem package. The transceiver die in the 525 has changed shape drastically, as you can see on the lower image. The intermediate frequency die has now moved out of the modem, in this case the X55, and is now a component of its own that also contains the data converters that were previously embedded on the modem. So there's only a digital interface from the modem to the IF chip. The two solutions do have many similarities, but also some differences. TechInsights has analyzed both the RF transceiver and RF IF die as part of the Transceiver Architecture subscription channel. This concludes the webinar, and I'd like to thank you for your time. And if there are any questions, please forward them on, and I will be happy to answer via email. Thank you.
That was a great demonstration of the findings and insights that can be gained from our architecture reports. Thank you very much for that, John. And for all of our attendees, we generate this content to make it generally available, and we'd like to see it in your hands because at the end of the day, the best people to identify the innovation and act on it and continually set the bar higher are you, the experts and the innovators within your respective companies. And we're always on the lookout for cellular components to profile, whether they are found in handsets or cell-enabled laptops or tablets, which with 5G and always connected devices, we certainly expect to see a lot more of them coming out in 2021 and beyond. And the content is always accessible online via our TechInsights platform, and we are known for very quick turnarounds, meaning that by the time a device makes its way onto the market, we try and get our hands on it, tear it down, see what's inside, and perform an analysis on it. And what this leads to is a platform that has a very continuous stream of content, meaning that there's quite often something there new to look at and analyze. So how can you get more content like this? Well, today we offer a few different subscriptions on mobile RF, which focus on cellular, 4G, 4G LTE, and 5G sub-6 and millimeter wave. Immediately available, we have the transceiver and envelope power tracker channels, for which we have a floor plan and architecture analysis on. The floor plan will show you things like functional layout, cross-section analysis, and manufacturing cost analysis. And then the architecture analysis is, for the most part, what you saw today. And now we expect the industry on aggregate to produce at least 8 transceivers and 5 envelope trackers that we can profile each year. And then all likelihood, we'll start with the leading chipset providers, but that's not to say if we find something interesting from a less prominent player, we won't profile that as well, because we certainly will. And the last thing before we wrap up is we recognize the importance of the full RF system, and we're looking to bring even more analysis to market on the front end and power amplifier modules in Q4 of 2020, as well as a complementing channel for the die we find within those modules, and that's the FEM and PAM die circuit analysis channel you see on the far right. So if you would be interested in learning more about the mobile RF content and roadmap we're producing, please reach out to us about our mobile RF product. We'd be very grateful for the opportunity to provide a more detailed introduction, and we can also provide info on pricing as well.
Thank you for today's presentation, John and Kyle. This concludes our webinar, and I'd like to thank you all for your time today. I would also like to provide you with some additional information you might find to be of interest. Our analysis is available through platform subscription products. We have provided a link above to more information about our Logic subscription, as well as to Tech Library, which offers access to TechInsights Technical Archive. And of course, we can also offer custom analysis if our library does not already contain the information you require. Why choose TechInsights? Founded in 1989, TechInsights offers an unparalleled combination of the latest technologies and analytical techniques, knowledgeable subject matter expertise in the broadest range of technologies, and the world's largest database of semiconductor analysis created over our 30+ years of operation. We serve our global clients from our headquarters in Ottawa, Canada, as well as from a number of satellite locations around the world. Would you like more information regarding our products or services? Please contact TechInsights by email at info@techinsights.com or visit our website, www.techinsights.com. Be sure to check out our website for our upcoming webinar schedule. Thank you for your time and have a wonderful day.